Asymptotic notation. Asymptotic notation are mathematical tools to represent the time complexity of algorithm for asymptotic analysis. Following three asymptotic notation are mostly used to represent the time complexity of algorithm. Three asymptotic notation are mostly used to represent the time complexity of algorithms. Okay, means time complexity of algorithm can be understood by three asymptotic notation. In three asymptotic notation, our first asymptotic notation is the theta notation. Our first asymptotic notation is theta notation. What is theta notation? I will explain you very easily, very friendly. Okay, let me consider. Okay, the theta notation bounds a function from above and below. Means theta notation is a notation which bounds the function from above and below. Okay, theta notation bound the function from above and below. So it defines exact asymptotic behavior. A simple way to get theta notation of an expression is to drop low order terms and ignore leading constants. Here we follow a protocol. Here we follow our rules. A simple rule is that we drop low order terms. We drop low order terms and ignore the leading constant which we have encountered in an expression. Okay, we understand an expression with the help of an example. What expression? Expression is this. 3n cube plus 6n square plus 6000. This expression is theta big of n cube. Okay, here we dropping low order terms is always fine because there will always be n naught after which theta n cube has higher value than theta n square irrespective of the constants involved. For a given function gn, let we consider theta of gn is following set of function. But here you understand this. We drop this term, we also drop this term, leading constant, we only have this term. Here n naught equal to 3. So this is big, this is not a big, this is theta of n cube, theta notation. So here we explain the our gn function, theta of gn function equal to this. F of n, theta of gn function is a function in n. Okay, there exists positive constants c1, c2 and n naught. F of n is such that there exists a positive constant c1, c2 and n naught such that our condition is here is that such that 0 c1 into gn is greater than 0, f of n greater than c of gn, and c of 2 into gn is greater than from f of n. Okay, for all n greater than or equal to 0. Above function, this means if f of n is theta of g of n, f of n is theta of g of n, okay, then the value f of n is always between c1 into gn, c1 into gn, okay, c1 into gn and c2 into gn, c2 into gn, f of n is always between that. So the definition of theta also requires that f of n must be non-negative for values of n greater than n naught. Definition of theta also resembles this thing because n naught is always here non-negative or non-zero number, okay, because if n naught is greater than n is greater than n naught or must be non-negative, then we can easily define our function. So here we have a graph. Here we can understand this with the help of a graph. Graph is this. Here we have f of n theta g of n, okay, and this we have c1 into gn is here and c2 into gn is here. And f of n is here. So here we can understand f of n is always non-negative, non-zero, and c1 into gn can be 0 and c2 into gn can be 0, but f of n always lie between c of 1 into gn and c of 2 into gn. So our second is notation for understanding time complexity is big O notation. That is very important. Big O notation is very important. The theta notation bounds a function from above and below, okay, but big O notation define an upper bound of an algorithm only. Big O notation bounds an upper bound of an algorithm, upper bound, okay, understand, from upper bound of an algorithm means we can only upper bound the algorithm. It bounds a function only from above. For example, consider the case of insertion sort. Example of insertion sort, okay, insertion sort. It takes linear time in best case and quadratic time in worst case, okay. In insertion sort, best case, in case of best case, it takes linear sort. In case of best case, it takes big O of n linear time complexity, and in case of worst case, it takes big O of n square, means quadratic time complexity. So we can safely say that the time complexity of insertion sort is big O of n square. Note the big O of n square also covers linear time. In big O of n square, we also have linear time. In between big O of n square, we also have linear time. If we use big O notation to represent time complexity of insertion sort, we have to use two statements for best and worst case. For insertion sort, time complexity, insertion sort, time complexity, okay. We have two things. One is the worst case time complexity of insertion sort. One is the worst case, very simple, worst case time complexity of insertion sort, which is big O of n square. And second, the best case time complexity of insertion sort, the best case time complexity of insertion sort is big O of n. The big O notation is useful when we only have upper bound on time complexity of an algorithm. Many times we easily find an upper bound by simply looking at the algorithm. Here we can define our gn function. Big O of gn is equal to f of n function when there exists positive constant, c and n not such that c and n not such that we have f of n greater than 0 and c into g of n greater than f of n. For all n greater than equal to n naught. So we can define big O of gn like this. We can understand this with the help of graph. Graph of this function is this. Here we have f of n is equal to big O of g of n, means we have c into g of n here and f of n here. So this intersecting point is what? This intersecting point is n naught. So this is big O notation. Our third notation is omega notation. What is the third notation? Omega notation. Okay. Just as big O notation provides an asymptotic upper bound on a function, omega notation provides an asymptotic lower bound. Asymptotic lower bound. Asymptotic lower bound. Omega notation can be useful when we have lower bound on time complexity of an algorithm. Okay, we have lower bound on time complexity of an algorithm. The omega notation is the least used notation among all three. Okay, we are using less and less omega notation. Okay, for a given function gn, we denote omega g of n, the set of function like this. Omega of gn, can we understand this f of n? Then there exists positive constant c. Okay, there exists positive constant c and n naught, c and n naught. Okay, such that c into g of n greater than 0 and f of n is greater than c into g of n. In case of big O notation, we have f of n less than equal to c into g of n, but in case of omega notation, we have f of n greater than equal to c into g of n, because omega notation provides an asymptotic lower bound for all n greater than equal to n naught. So this is the function. We can understand this with the help of graph. Here we have c into g of n here, and f of n is here. So this intersecting point, we have this n naught. Here f of n is equal to omega g of n. So these are the asymptotic time asymptotic analysis, asymptotic notation for understanding time complexity. Okay, guys, subscribe this channel, and you also join our course, our 6-month course or our 10-week course. With the help of our course, you can take a placement, a better placement up to 40 LPA. You only pay after placement. We are not asking any money earlier. Okay, after placement we are asking for money, so you can join our website. Our website is www.coderjobs.com. This is our website. You can explore our platform and take our course. Thank you, and also subscribe this channel for more. Just like this video, this explanation.